Hello, 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 everybody, and welcome back. Welcome back, or welcome if this is the first video you're watching. I'm going to be going through another quiz from 1600 when it was taught in 2010. Very similar material, and I just wanted to get some more examples out there and the sort of questions that we like and have liked for the last almost a decade. But just a fair warning, this is not comprehensive. This is not going to be, well, these questions are exactly the midterm is exactly these questions. No, 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 they're just supposed to be extra little questions to get you thinking, get you in the mood for some linear algebra. Of course, you should be trying the practice problems that we've assigned, looking over problem sets from the past if you guys have access to those or wrote those down. And, of course, come to office hours if you're having difficulties or any questions about the material. But here we go. Question number 1 on this quiz. It's a 3-question quiz. And so here's one. Write the vector 8, 5, 11 as a linear combination of 1, negative 2, 4, and 2, 3, 1. Okay. So how am I going to make them a linear combination? Well, what does it mean to be a linear combination? It means I can find scalars, a and b, that satisfy this equation here. Okay. Now, one thing we could do is turn this into a system, make AB sort of a solution vector, and get a system of equations, and that's fine too. I'm not saying that the way I'm about to do this is the only way to approach this question, but with only 2 vectors, I think I'd rather sort of write it out a little bit more. This guy's a 4, isn't it? There we go. 3b and 11a plus, or sorry, 4a plus b. Okay, now nothing immediately is springing out at me, but okay, well, I was trying to avoid it, but you can always do a linear combination of vectors. Sometimes when it's small enough, if there are zeros or things like that, there's some numbers that you can pick off really easy. I mean, this is only listed as being worth 2 points. But if worse comes to worse, you can always turn this into a system. So we'll have 1, 2, 8, negative 2, 3, 5, and 4, 1, 11. All right, let's go to work. So row 2 plus 2 row 1. 1, 2, 8, 0, 7, and 8 plus 16, 21, 4, 1, and 11. And so right here, I can actually see that, oh, this means that a plus 2b is equal to 8, fine. 4a plus b is equal to 11, but now I've got just 7b is equal to 21. B is going to be equal to 3. I don't have to completely row reduce the whole thing. Just get it to a point where I can solve. Okay? They're not saying show off your brilliant row reduction skills. Okay? If they did, that would be part of the question, or it'd be like an A part or something. B's got to be 3. Okay, plug it into the first equation. A plus 2 times 3 is equal to 8. A plus 6 is 8. A is going to be 2. And we can check. 4 times 2 plus 3 is 8 plus 3, which is 11. So, our final answer, we were just asked to show a linear combination. 8, 5, 11 is going to be 2 times 1, negative 2, 4, plus 3, 2, 3, 1. There we go. Just write it as a linear combination. Well, there I did it. Okay. Used a little bit of row reduction, although, maybe a guess and check would have been fine, but I wouldn't recommend guess and check because, well, sometimes you don't check it all the way completely, and sometimes the marks are for your elimination method. Okay. So there we go. Question number 2. Feel free to pause and try this one out if you want to. Read off the screen before I get to it. But question 2, state if these are true or false. Okay. A. If A and B are symmetric matrices, then A plus B is triangular. Triangular. Okay. So remember what a symmetric matrix is. It means if I transpose it, I get the same thing. Okay? And triangular, remember what that means. That means it's either upper triangular, in which case, you know, I'll do a couple examples to really make it clear. So, you know, here's an upper triangular matrix. And, you know, here's another upper triangular matrix. We'll make these numbers a little nicer. Okay. Now you might be grumpy about that 0 in the middle there. If I can ever get my pen to write thinner, or to erase thinner, I'd be so happy. But upper triangular just means that if I sort of section off this upper triangle, everything else is 0. It doesn't mean there aren't zeros up here. And of course, a lower triangular matrix would be something like 1, 1, 2, with zeros above the main diagonal. Doesn't matter what's on the main diagonal or below it. Okay, so those are what triangular matrices are. Now, symmetric matrices are pretty powerful. And, you know, if we do a little experimentation, we might get something like, well, 1, 1, 1, 1, 1. That's symmetric, because if I transpose it, if I flip along the main diagonal, I'll still get 1, 1, 1, 1. Okay? So we might say something like A is that. They didn't say A and B had to be different, but these guys here are symmetric. But A plus B is going to just be 2, 2, 2, 2, which is not triangular. And that's all it takes, so this one's false. Because they said if I took two symmetric matrices, I'd get a triangular one when I add them, and I don't have a triangular matrix. Of course, another answer to this would be, well, couldn't you just take A and B to be different sizes? Then A plus B isn't even defined. Okay, that'd be another way to do the question. Okay. B part. If A and B are diagonal matrices, then AB is diagonal. Okay. So, well, what does it mean to be a diagonal matrix? So, a diagonal matrix has sort of A11, A12, A1n, all the way down to AN1, ANN. But the only thing that isn't zero, the only non-zero things are going to lie along this main diagonal here. Okay. So I would say this one here is true. Here's an example. Now, remember, examples are not proofs. But what happens when I do this calculation? Well, 2 and 3 is 6 plus 0 times 0 is 6 plus 0, which is 0. I'll get zeros here, and I'll also get a 1 here. Examples aren't proof, so this is not enough to justify, because remember in 2010, we asked for justification. So what would I probably need to say? Well, let's say A is A1J, and so and B we'll write as B1J, and we'll write AB as CIJ, and A and B diagonal. So AIJ is 0 for I not equal to J. BIJ is equal to 0 for I not equal to J. And now suppose we look at CIJ. You know, the ij entry of A times B. Okay. Well, this is AIK or AI1 and I specifically just want to show that this is equal to 0. So this is AI1 B1J plus AI2 B2J plus it just keeps going on like this. AIN BNJ. But if I isn't equal to J, then for any term here, it always looks like AIK BKJ. either k isn't the same as I or k isn't the same as j. It can't be equal to both because then I and j would be equal. And so ik is equal to 0 or bik. So aik or bik is equal to 0. So aik bkj equals 0. So cij equals 0 plus 0 plus a whole bunch of zeros, and so is itself 0, as long as it's not on the main diagonal. So yeah, AB is diagonal. And there's my quick justification. You know, this wasn't an easy question here. It's not that hard to see that it's true by looking at a bunch of examples, but it's a little trickier to prove, a little trickier to justify. And, you know, maybe you get a half mark for an example or two. But remember, examples aren't proofs. And now, for 3, show that for any vector v, the set of vectors u with v dot u being equal to 0 forms a subspace. Oh, it looks like they had a typo this here. Subspace of Rn. Okay. Poor TA probably got quite red-faced when he had to present that one, but oh well. Wasn't me. I think I was section 5. That was a long time ago. Okay, so we want to show that this forms a subspace of Rn. Okay, so what does it mean to show that something's a subspace? Well, we have to show that 0 is in the space. So actually, let's show that. So let's be fancy about this. Let's let S be the vectors in Rn so that this dot product is 0. So first, let's show no matter what v is, anything dotted with the 0 vector is 0. So 0 is in S. Okay. Now suppose we had x and y were in S. We need to show that their sum is in S. So I'll make the quick observation that v dot x is 0 and v dot y is 0. Why? Because they're in S, and by definition that's what it takes to be part of the S club. Okay, so now if I dot v with x plus y, well, we have to think way back when to 1.2 when we covered that material, but you're allowed to distribute the dot product over a sum, and I know each of these is 0, so we get a sum of 0. So it turns out x plus y is also in S. Now finally, we need to show that any scalar multiple of something in S is also in S. Okay, so, well, again, v dot x is 0. Now v dot cx, we have to remember, again, that the scalars can pop out of a dot product. So this is really just c times 0, which is 0. So cx is in S. And that's all it takes. Remember, to be in a subspace, you just had to show 3 properties. 0 was in there, any sum of vectors in S was also in S, and any scalar multiple of S, of something in S is also in S. And that's all it takes. So this question was probably worth 3 marks. Maybe it was worth... yeah, it looks like it was worth 4 marks because these were worth there were always 10 marks available on a quiz, so probably 3 marks and maybe a little therefore statement. But there we go. Okay, so actually, you know, checking that something's a subspace isn't so bad. You just sort of go based on the definition of what they're talking about and the definition of what a subspace is. Those 3 properties, if any one of them fails, you're not looking at a subspace. It makes great true-false style questions as well. Okay. But that does it for this most recent, well, I say recent, this particular quiz. And, you know, if I find some more time, I'll post some more quizzes or more examples of going through interesting-looking questions from 1600. But continue having yourselves a wonderful reading week, and, you know, I'll do the same. Okay. So long for now.